Okay, so in the last video, I described, here, let me adjust that just slightly. So in the last video, I described Ohm's law and I gave both macro and microscopic descriptions of it. So we described it from the point of view of being inside a wire, and you had a current density describing the electrical flow, and then and then I related the, um, the current density to the internal electric field in the middle of the wire. And then I also kind of zoomed out and took the macroscopic point of view and relating the drop or change in voltage, or sorry, change in potential across a wire or device, really, and the current. And that led to Ohm's law, which said that V equals IR in its most common uh, incarnation. All right. So today I want to talk about, or in this video, I want to talk about the power associated with moving charges around, and or the work that being done on those charges, things like that. And that's going to lead us to um, the concept of um, Kirchhoff's second law, which is called the loop rule. And that's kind of our stepping off point for getting into circuit analysis. So what we have is the following situation. So, you're moving charges around inside a wire, and that doesn't happen for free. You have to push them through, which means you're doing work on them. So the idea would be, if you move a little bit of charge through a change in potential. So if we have a change in potential, and I'll just call that change V. I won't write delta V, I'll just write V, because in circuits, everything is a change in potential. Nobody calls it delta V, or basically, when they say the words, they'll say a difference in potential or voltage drop or something like that. But when they write it down, usually they just say V. And we're going to push a little bit of charge around. Well, so if you push charges around in through a change of potential, then the work you do becomes the change in potential energy. So basically, you're going to say that there's a little bit of work being done when I push a little bit of charge through a potential there. So it really looks like our potential energy formula. All right. And that's fine. Now, last time, or maybe 2 videos ago, we learned how to relate little bits of charge to a current over a little bit of time. So I can say that this is nothing other than a work equals the current. Well, how about I do this? I'll write this as dq dt times dt times the potential. And then I can say, pulling that together, I can say that dw equals I times V times dt. Okay, so what this says is that we started off by thinking about individual bits of charge, but really you could think of it as just a current flowing over a teeny tiny bit of time. And so to make a current flow through a potential difference for a little bit of time, that takes work. Okay, it doesn't want to happen just on its own. And we can then divide everything by time, and we can say that the power, capital P, not the polarization vector and not the dipole moment vector. I apologize, I'm just out of letters. The power associated with moving the current through a voltage is dW dt, that's the work. So this would be the power needed to be supplied to push it through, if you want. Or in steady state, that means it's also the power radiated out in the form of heat. Anyways, equals I times V. So PIV, P equals IV, PIV. Okay, so that means that for a device with a current acting through a voltage or passing through a voltage difference, the power is going to be the current times the voltage. All right, that's handy to know, PIV. It's even, if we combine that with what we learned about Ohm's law, so we have PIV, we also have V equals IR, so we can come up for ohmic materials, so resistors or something that behaves roughly like a resistor. Then I can just do some algebra here and I can write, I don't know, I can say P equals I squared R, or I could say P equals, if I solve for I and substitute, I would get V squared divided by R. And that's kind of interesting. If you have a device which has fixed power, no, take it back. If you have a device which has fixed voltage, like a battery, and then you hook it up to a wire or something with very small resistance, then what's going to happen is, because the resistance gets small, in order to maintain the constant voltage, even though there's little resistance, the power that has to be supplied is huge. And that's what happens if you take a battery and you hook it up, you make a short, we call it, where you basically connect something with very little resistance or a wire between both ends of the battery. You'll notice that the battery gets hot because it's having to really provide and deliver a huge amount of power. I think that's the most common application of that. So that's kind of a standard example. All right. Okay. That's fine. Now, next up, there's a phrase that comes up. It's called EMF, or electromotive, force. Okay, the EMF of something. It's not a force. It's just a misnomer. I think it goes back to a time when they didn't really know what was going on, so they kind of just defined quantities, and it kind of sometimes maybe acted like a force a little bit, so that the name stuck. All right, and we still use it. It turns out it's actually the work per unit charge. So remember, we're saying that dW is dQ times the potential difference, and but more precisely, what we call the EMF is going to be defined as the work done on a charge per unit charge. Okay, so that's the definition of it. And yeah, so that's really just the definition of it. All right, so, but it has units of volts. So, all right, so then you can relate that to everything else we've been doing, and you could write that as dW dt I want to say this in the right way. Oh, sorry. Right. I could say, take it back, turn it around. I could say that the little bit of work, instead of writing it that way, I could write it as um, I could write that as EMF times dq, which I got to write as EMF times I dt, and right. Okay. So this is from the work side of it. On the other hand, I have the kind of potential energy side of things, and the two have to be the same. So what this allows me to say is that using the conservation of energy, that I have to have, I can write in different ways. Basically, you have to have that E times I is the same as I squared times R. So you're basically saying, relating the voltage drop, or sorry, the potential drop side to a work side. So a potential energy language to a work being done on the system, they have to be the same. Or so in particular, if you have a resistor, you can say that you can just rewrite things. You can say things like I equals EMF over R. And this would be for a circuit where, this would be in the context where I had, say, some device called a battery, which delivers it kind of does work on a charge. So as you move charge from the negative side to the positive side, you're doing work on it, and then you run it through a resistor of some resistance R, and they give rise to a current I. Basically, what you're saying is that all the energy has to be accounted for so that the work done here is related to the drop in potential as you go across the resistor. Okay, so that's the idea. The current in the wire must be related to the voltage on the battery, or the EMF, and the resistance. Okay. All right. So here's the general statement of energy conservation. Or, well, that's what you're really doing. Basically, it all has to add up. And when you're running a circuit in steady state, then what you really have to have is that as you go around a circuit is just a string or a series or a combination of different little electric devices. And the statement is that if you add up all the changes in potential energy as you go around a circuit and you get back to the same place, they have to add up to zero, as long as there's nothing leaking out into the environment. So in particular, so that just becomes what's called Kirchhoff's second law. Or sometimes called his loop rule, or sometimes called the voltage rule. Okay, and the statement is, you could have a circuit, it can be made up of many different blocks, different things. And they could do lots of things. And you could imagine that as a current flows around, doing whatever, as electricity moves around, you would have, you'd have a voltage drop or voltage change here, V1, and you'd have a V2, and you'd have a V3, and you could have a V4. And the statement is this: as the charges move around, The statement of energy conservation means that basically if you go around and you get back to the same place, then you better have the same potential energy that you started with. Or if you phrase it in terms of voltages, it means that if you, as you go move around inside the circuit, the sum of all the changes in voltage better add up to zero around a closed loop. So the loop rule says the following: for any sort of circuit, the sum around a loop, and it's any loop, it doesn't matter, of all the voltage drops will equal zero. That's really just a statement of energy conservation. Okay. So that's Kirchhoff's second law. All right. So we already saw Kirchhoff's first law, which was his current rule. That said that whenever you had a junction, that the current in equaled the current out. And basically, if you're really dedicated, you can just apply the two rules over and over and over, and you can figure out every current and every voltage drop and all the power radiated through every component in any arbitrary circuit. So, okay. So I think I'll stop there in this video, and the next video we're going to start using this to deduce properties of circuits. Okay.